Welcome everybody to our distinguished webinar series on artificial intelligence and cybersecurity. Today's talk is leveraging nonlinear dynamics for efficient brain-inspired computing using physical reservoir, featuring Dr. Sakib Hasan, assistant professor at the University of Mississippi. Dr. Sakib Hasan joined the Department of Electrical and Computer Engineering in the University of Mississippi as an assistant professor in the fall of 2019. He received his Bachelor of Science in Electrical and Electronic Engineering from Bangladesh University of Engineering and Technology in Dhaka, Bangladesh in 2009, and the Ph.D. degree in Electrical Engineering from the University of Tennessee, Knoxville in 2017. His research interests include secure nanoelectronic circuit design, neuromorphic computing, nonlinear dynamics and chaos, semiconductor device modeling, and VLSI circuit design. Dr. Sakib, it's a pleasure to have you, and with that, the floor is yours.
Thank you, Mr. Jamison, for your nice introduction. So today, let me first share my screen and I'll start with my talk. So can everybody see my screen?
Yep, it looks good.
So today I'm going to talk about how we can use nonlinear dynamics in physical system using a relatively new computing paradigm called physical reservoir computing. So without further ado, let me start. As Mr. Jamison just introduced me, I am at Ole Miss, University of Mississippi. I'm an assistant professor. And one of the things that I have been researching on is brain-inspired computing, sometimes called neuromorphic computing, because we take a both hardware and software integrated approach to kind of replicate the energy efficiency of brain. And with that regard, I started working on neuromorphic computing, which is a pretty broad field. And I started working on reservoir computing 4 years ago. It came relatively new, and there is some interesting things that you can do with physical system that really attracted me. So I'm going to talk about that. So this is how the presentation is going to go. So we are at our lab collaborating with Pennsylvania State University, Dr. Joseph Nazem's lab, who makes biomolecular devices, both memristors and memcapacitors. And in our lab, we try to use that for computing purpose, for reservoir computing. And kind of we do a collaboration back and forth. So we have been doing this collaboration for a while now, for 6 years, and have been doing the reservoir computing part for last 4 years. So we have some interesting results that I am going to show. For the sake of time, there are many other physical reservoir computing work in the literature now, especially the field has boomed in the last 7-8 years. I'm not going to be able to cover all of them, but there is a great book that recently came out, which will be a great reference, and there are some review papers. So I'm going to suggest that and mostly focus on my work, and finally some questions for open questions for physical reservoir computing for anybody who is interested in this field. So let me start with the motivation. So most solid state devices have little resemblance to bio counterparts at the mechanism level and require significantly large power hungry CMOS circuitry. So what the problem is this, that maybe most of you listening are aware of this, that semiconductor technology are facing a significant problem because we are kind of used to exponential increase in computing over the years, and that is due to something called Moore's law. So every 18 months to 18 to 24 months, the computing power gets doubled, but the price does not increase, and you get more speed and so forth. But that's all because of 3 separate things, often termed the same way. But there has been this computer architecture called von Neumann architecture, where memory and processing are separated. And it's a very simple way to program the computer. That's why it has been popular since the beginning. And then there is the Moore's law. So transistors became smaller and smaller as time went by. On top of that, there is the power thing, that even though transistors became smaller, so you can put more transistors on a chip. Just to put an example, that in 1971, when the first commercial microprocessor came out, there were like 4,000 transistors. And now we have several billion transistors in modern chips. So going from 1,000 to billion, so that's almost unbelievable, the level of scaling that has occurred, right? But the natural question is that if you put 6 orders of magnitude more computing elements, wouldn't it cost much more energy, and wouldn't it melt the chip? The reason it does not melt the chip is not really Moore's law. This is another thing called Dennard scaling, that if you can reduce the voltage as well as the size, the electric field remains the same. In fact, the transistor gets a little bit faster because the distance between source and drain gets smaller. And the energy per transistor actually goes down. So energy density remains kind of the same. So the chip does not melt. So you get same energy cost, orders of magnitude more compute, and orders of magnitude more speed. Now, that's a very lucky coincidence that happened with CMOS transistors and our current computing paradigm. We got very lucky and were able to sustain like exponential growth over 6 decades. It took a lot of engineering and science to achieve this, but we could do this. And in the history of humanity, this never happened to any other industry. This only happened to this computing industry. But we are at a crossroad. Many scientists and researchers working in this field, including me, believe that this time around, we are really at a crossroad. We need to look at alternative paradigms for computing. The first thing is Moore's law is slowing down, and we are actually hitting some physical limits. So we are building transistors at 10 nanometer, 7 nanometer channel length, and going below that with current field effect transistor technology, it seems improbable to say the least. And you can see this, like every 18 months to 18 to 24 months, new technology node coming. That's not happening anymore. And I don't foresee this. So Moore's law is slowly coming down. That scaling thing is slowing down. To make matters worse, Dennard scaling, which made the energy thing work, actually died long time ago, 15 years ago. Many people are not aware of this. So we have hit something called the power wall. The way computing industry solved this problem is they went from single core to multi-core processors. So the single core frequency did not increase after 2006, if you notice. But they solved this with multi-core, a little bit different architecture. And then we have the memory wall, sometimes called the von Neumann bottleneck. So having this separate memory and processor, now what happens is that more energy is lost during traffic from memory to processor than doing the actual computation. And now with the emergence of big data and AI, which are massively parallel, because neural network-based AI is basically brain-inspired. And this is massively parallel, but our von Neumann stored computer architecture is sequential. The time when we have made AI to work, neural network to work, our hardware doesn't support our software, and we have a tremendous explosion of data due to Internet of Things, and also like accumulated data through internet over the last 20, 30 years. So we need to do a lot of compute. We need less energy per compute, but our technology is kind of breaking down at the worst time possible. So if we keep doing the same thing over and over again, it's unlikely that we are going to sustain this exponential growth. So that's why many people are looking forward to a different kind of computing, and brain-inspired computing, neuromorphic computing is one way of doing things. There are other stuff. People are doing photonic, which is very promising. People are doing quantum computing, which is also very promising. But I've been focusing on neuromorphic computing. It's trying to replicate the energy efficiency of brain. So brain can do a lot of compute with very little energy. So to give you an example, that most of you probably have heard that when AI was exploding, there was this thing like we defeated AlphaGo the AI program defeated AlphaGo champion, and that was a huge thing, right? But what the newspaper did not highlight is that the computing system that was defeating AlphaGo human champion was actually consuming 6 orders of magnitude more energy than the human being. So yes, so if you say that it is defeating human being, it's true in one regard in actually beating in AlphaGo. But as far as energy efficiency is concerned, human beings are much more superior to modern computing chips. Energy has become a huge issue. It was not originally a huge issue when the computing revolution started, but now energy efficiency is a huge thing. So in next generation, people are trying to come up with more energy efficient computing, and brain is obviously a very good example because brain is so energy efficient. So people are trying to mimic different aspects of brain in hardware. The very difficult thing because we are at the infancy of learning about neuroscience. We don't know a lot of algorithms, what actually happens, why it happens, and also a lot of fundamental building blocks in brain. It's not obvious how to replicate that in solid state chips. Anyway, so this is kind of the backdrop of where I come to this. And on this thing, like one element emerging device that has become very popular, and there has been some controversy about the naming, but for our purpose, that's not important. So this device is called memristor or memory resistor. Basically, for our purpose, it's a resistive device with some memory. And there are some corollary to this device, like resistive, capacitive memory, inductive memory. So any of the passive devices with memory, how can we use that for more energy efficient computing? Now, neuromorphic computing deals with a lot of different class of algorithms. In this talk, I'm going to focus solely on reservoir computing. So reservoir computing is a simple and highly efficient algorithm, which has recently come into being like 20 years ago formally. So, for example, this is a human brain, and you guys probably have seen these kind of things before, that different parts of human beings, how neurons communicate with each other through synapses and so forth. But there is the important thing is that there are neurons in human brains which has a binary behavior. So if the membrane potential goes over a threshold, there is an action potential or a spike. Otherwise, there is no spike. So neurons in brain are spiking. So they either spike or not. However, in the artificial neural network or deep neural network that has become very popular, the neurons are not like that. They are continuous valued output. It's not like 0 or 1. They are real value between anything between 0 and 1, usually sigmoid, tan hyperbolic, or ReLU or rectified linear unit. These neurons are used in artificial neural networks. So it's a very abstract version of the human neurons that we use in artificial neural network. Now, we talked about memristor a little bit. So memristor was fourth fundamental circuit element, as Leon Chu phrased it in 1971. It was an axiomatic approach, but then in 2008, there was a big experimental demonstration. So Stuart predicted this in 1971, and in 2008, Stanley Williams group in HP Labs demonstrated a device which kind of matched with that thing. Again, there is some controversy about it, but the main thing is that these are devices which has non-volatile memory that Stanley Williams group showed. So basically, you can program it, and even if you take the power away, it remembers things. So it is a good memory device. So people are interested in this. Now, as it comes to reservoir computing, that the idea is very, like at the first glance, look very simple and counterintuitive. So you guys have all seen neural network by now. I think it's a huge thing now. So you give an input. There are lots of neural layers of neurons. Different layers do somewhat different things, but there is a global learning algorithm like backpropagation and gradient descent based backpropagation, and then it finds out the weights or synapse, the abstraction of synapse, and that's how it solves the problem. Now, the interesting thing is this, that in this thing, all the connections, all the synaptic weights are trained. The reservoir idea is kind of like this, that what if we have an input and then we have a recurrent neural network, not feed-forward neural network. So like convolutional neural network for static image classification, these are feed-forward networks. So input goes only from left to right. The signal flow is from left to right. However, for some sort of temporal problem, when you need memory of what happens before, you need memory of past inputs, let's say. What would be a good example? So, for example, audio signal, like when we listen to someone, the sounds mean something in the context of previous sounds. When you read something, so natural language processing, a particular word, the meaning of a particular word depends on what appears before it and the previous sentence and even the previous paragraph. So we all kind of intuitively understand this, that the meaning of a lot of things depend on the context. So you need to know the past history to fully appreciate the present input. So this kind of feed-forward neural network are very static. There is no dynamic nature to it. There is no memory to it. So whatever input comes, it produces an output based on that. If this next input comes, it does not remember anything about previous inputs. That is not good. That is not sufficient for temporal data processing, right? So people have come up with solution called recurrent neural network. And you probably have heard about LSTM, long short-term memory network, or GRU, gated recurrent unit. So different version of recurrent neural network that are available in the literature that solves this problem, right? And out of this recurrent neural network literature came this idea of reservoir computing. So at its core, the input goes to a recurrent neural network, which is called a reservoir, and its output is going to a readout layer, output layer. Now, the twist is this, that the input to reservoir connections, those weights are not trained, they're randomly chosen. Similarly, the reservoir connections, internal connections, are also randomly chosen. Only thing that is trained is the single layer readout, usually a single layer, but you can use a multi-layer neural network as well. But only the readout layer is trained, which is a feed-forward neural network, which is easy to train. Training recurrent neural network is much harder because you have to do backpropagation through time. It's a much more costly training procedure, and it also suffers from exploding gradient or vanishing gradient problem. So it was a very interesting idea that you don't need to train the difficult part, the recurrent neural network part. You can just choose random weights and it still works. Now, why does it work? The reason it works is that if you have a high dimensional recurrent neural network, you take a input, let's say like 5-dimensional input, and it projects it into 500-dimensional space. And in that higher dimensional space, it retains some memory of previous inputs, and it is a nonlinear projection. So these 500 outputs are, not linearly dependent on each other. So now this high dimensional space, apparently things are linearly separable. So you can use a single layer, or even if they're not completely linearly separable, you can use 2 layers or simple feed-forward neural network, which can be easily trained. So this is very reminiscent of another machine learning technique called support vector machine, where you project things to a high dimensional space where things are classifiable, where the original raw data was not classifiable. So it kind of combines the best of support vector machine and recurrent neural network and comes up with a very simple training cost algorithm. So it became very interesting. People became interested for temporal data classification or prediction problem with reservoir computing. So, and people implement this reservoir computing originally. The fundamental idea came in 2001 and 2002 from 2 separate groups who simultaneously stumbled into the same idea. So there is this group from Harvard Eger who introduced something called equistate network, and then Wolfgang Mass, who introduced something called liquid state machine. The main difference is that in equistate network, these neurons are artificial neurons, like sigmoid or tan hyperbolic. And for liquid state machine, these neurons are spiking neurons. So basically, equistate is artificial neural network, and liquid state machine is spiking neural network. And currently there are research in both direction, artificial neural network and spiking neural network. So some people work on ESN based reservoir, and some people work on LSM based reservoir computing. However, then people realized that these are not the only way. So these are just software reservoir computing, like the algorithmic approach to reservoir computing. But then gradually people realized that Well, we just need a nonlinear dynamic system. It does not have to be neurons connected with synapse with feedback connection. Any system that has certain properties, fundamental property is called fading memory property. So it has to remember past memory, but not infinitely past. So it has to gradually forget. The memory has to fade. Otherwise, like something that happens 1,000 steps before will always have a lasting impact, and that's not good. So it has to have fading in memory, but fading memory, and it has to have nonlinearity and higher dimension. These are fundamental properties. So any nonlinear system, dynamic system, if it has these properties, can be used as a reservoir. So this is kind of the birth of physical reservoir, or sometimes called PRC, physical reservoir computing. So any physical reservoir can replace this recurrent neural network. And let me just make it. So any physical reservoir can replace this recurrent neural network, and we just train the readout layer with this thing. And this realization led to a lot of new reservoirs in the last 10 years. And it's currently a very booming field. A lot of people are exploring different systems. So the most interesting systems probably was people did reservoir with water buckets. So how the water flows, it literally a liquid state machine. So it was a liquid flowing up and down, and that nonlinear dynamics was capturing something, right? That was probably the most exotic reservoir. But people did reservoir using biomolecular device, which we are going to describe in the next slides. A lot of electronic implementation, a lot of photonic implementation, um, mechanical implementation, MEMS, micro electromechanical system implementation. So different physical systems, DNA reservoir. So different physical systems have been shown to do reservoir computing. For the sake of time, I am not going to cover those things. But those who are interested, very recently, there is a great book on reservoir computing that came out. 2021. In fact, the pioneers all contributed, most of them contributed to this book. So it's a very rich collection on what happens in the last 20 years of reservoir computing. And a big part of this book is actually on physical reservoir computing, different types of physical reservoir computing. So I'd highly recommend everyone to find out this book. I'm going to actually cite several chapters of this book. So that will be in the slides. So if you're interested, you can find that. Another very good review came up from another active researcher, Tanaka, is a review of physical reservoir computing, which is a very comprehensive review of what is happening on physical reservoir computing. So if you are interested about learning about different systems, those are very good resources. But for the sake of time, I am going to focus mostly on our group's work, and then finally some open questions, some challenges and opportunities for PhD that need to be addressed. Okay, so this is the idea that instead of conventional neural network, we're trying to do reservoir, and for that we need some interesting physical systems. Now, what really happened was that Dr. Nazem and we have been collaborating before I came here actually at Ole Miss as a postdoc, and there was this device called biomolecular memristor that we have been collaborating on. So this is alamethicine doped biomolecular memristor. Don't worry too much about the details of this device right now, because it can be done with different other memristors as well. But the main thing is that these are like water droplets connected together. There is a lipid monolayer, and at the interface, there is a lipid bilayer. And so this is called DIB, dipole induced bilayer. And if you have some sort of peptides like alamethicin, then what happens is that if you apply a voltage greater than a certain threshold voltage, suddenly channels are created so that ions can flow. This is very similar to how electrical conduction happens in human brains actually. So that was it was very interesting for us to explore. So, and we kind of model this thing. Again, there are two state variables, Na, which is the pore concentration, and Am, which is the area. So basically, when you apply a voltage, the number of pores channels increases, and also the number of the area of this by this layer also increases. Anyway, without getting bogged down in the equations and the details, just to remember, just to say that this is a dynamical system. It is a nonlinear dynamical system. So how can you use this for reservoir computing, right? So just to show you an example that why this is useful is that we are doing a voltage sweep here. So we are going from 0 to 150 millivolt and coming back to 0. And we see there is a hysteresis. So this is the memory part, the fading memory, which is important for reservoir computing. So this is shown here as well. So you are applying a sequence of pulses, and as a result, the conductance, as you can see, when you apply a voltage, conductance increases, then it decreases for a little bit, and then when you apply another pulse, this conductance increases again. The meaning of this is this, that if you apply successive pulse, they are all same amplitude. The conductance does not remain static. If it was a normal resistor, a static resistor, well, the resistance does not depend on voltage, what happened before. But in this particular case, the resistance or conductance does depend on previous memory. So for the same pulse, you get different conductance at different time. This is in neuroscience language, this is called PPF, paired pulse facilitation. So if you have two pulse paired with each other, the second pulse produces more current than the first pulse. So that's why this is called facilitation. There is also a counterpart called PPD, or paired pulse depression. In this case, the second pulse actually produces less current than the first pulse. Right? So this is called short-term plasticity, short-term memory. So you have a little bit of fading memory of the past. And we thought that, okay, it seems like the response is nonlinear. The voltage to current response, as you can see, is nonlinear. There is fading memory. So it should be a good candidate for reservoir computing. So we kind of connected the dots between the device and the computing architecture. And just to show some example that different binary sequences, if you convert them into voltages, you see diverse conductance response. So it can distinguish between different sequences, basically. The important thing is this. Similarly, there is another device that we explored. It is kind of the same device, but if we get rid of the mem capacity, the lipid, in the lipid membrane, there is the peptides, L-amethicin. So let's say we get rid of the L-amethicin, and if you have an organic solvent and you have these two water droplets, if you apply a voltage now, the area increases, but also the thickness also decreases. So you can describe this using a second order nonlinear coupled differential equation. And the two state variables are R, the radius or the area, and the W, the thickness of this capacitance. And this capacitance changes with time. So this is a MEM capacitive device where geometrically capacitance changes. So you can think of it as a parallel plate capacitor where the area is increasing due to voltage, and also the thickness or the distance between the plates decreasing due to this voltage. So if you apply high enough voltage, capacitance gradually increases. But if you take the voltage away, it goes back to the original thing. So an important part about both our MEM resistor and MEM capacitor is that they are volatile. Most of the research on MEM resistors and MEM capacitors are on non-volatile memory, right? Because these are the most important things for memory application. But for reservoir computing application, actually, we don't want non-volatility. We want volatility, right? We want fading memory. So volatile memory resistors and volatile MEM capacitors are actually more suitable for reservoir computing. So we thought that, okay, both of our devices are volatile memory resistors and volatile MEM capacitor. So why not use them for reservoir computing? So we are going to show some results, and I'd like to thank my collaborator and the graduate students, our graduate students who have done the hard work. And so let's look at some results. So first of all, reservoir computing has been very effective because it's a nonlinear dynamic system, and a special case of nonlinear dynamics is chaos. So people have shown that reservoir computing has performed well for predicting chaotic system. So in our lab, we also do research on chaotic systems. In fact, my last talk here was on chaotic system. So we thought that let's connect the two worlds. So we worked on discrete time chaotic system. And these are called chaotic maps. So we try to predict some chaotic maps with reservoir computing using our devices. So this is an example of a chaotic system. Uh, there is something called a bifurcation parameter. And if you change the value, things start from a fixed state, become a period of 2, then period of 4, and eventually becomes chaotic. And different systems has different bifurcation diagram, different dynamics, basically. Okay, so now let's try to predict this. So the way we are doing this is that we are including the input. We have to encode the input into some voltage that our device can handle. And this is similar to other memristive reservoir computing world. So each memristor, each physical system has a certain voltage range where it works properly. So you have to encode the raw input into that voltage range. There are different encoding that are possible, but we are doing simple linear amplitude encoding. And based on that, we can do the classification. Now, the problem with our reservoir is that we usually have parallel multiple memristors or mem capacitors. So these nodes are not coupled, right? But in actual reservoir, nodes are supposed to be coupled. It's a coupled dynamics, more complex dynamics. So there is a solution that Appleton and others came up with in 2011, that if you have a dynamic system, a delay-based dynamic system, you can do coupling in time instead of space. So having separate neurons, you can have a single neuron, but you can use a mask. So basically, it's a time multiplexing. So masks are usually binary, but you can use any mask. And the inputs are multiplied with this mask. And as a result, you get a different sequence of value. And then it goes to the reservoir. So let me show you actually a example. So let's say each of your data input has a delay of tau. So after tau, the next data comes. But for each input duration, you want to make 4 virtual nodes. And in this case, I'm showing actually 1, 2, 3, 4, 5 virtual nodes. And so we divide the tau into 5 parts, and the smallest portion is called theta. So 5 theta is equal to tau in this case. Now, in this case, we are showing binary mask. That means the mask can have 2 values, +1 or -1. If your mask length is 5, and each mask can take 2 values, there are 2 to the power 5 combinations that are possible. So basically, based on which mask sequence you choose, you get a different response from the memristor. And since you can choose 2 to the power 5 or 32 different mask sequence from the same input and the same memristor, you can put them parallelly. Each of them is driven by a different mask. So 32 different memristor will produce 32 different response. So from the same memristor, same copy of the same copy of the memristor, you can make 32 copies and get 32 distinct reservoir output by using this time multiplexing. Also, these reservoir nodes, these virtual nodes, are interconnected. Not all of them are interconnected. Like these 5 nodes in each memristors are interconnected, but it's not bad. So that's why you can get a lot of reservoir output, high dimensional output. And this is the technique that Appleton started with delay coupled reservoir. And then in 2021 for memristive system, there is a group from Tsinghua University who demonstrated this memristive system. So we kind of following on their work and replicating that. And they did it with binary mask. So we kind of improved upon that, but I'm going to show this later. So now we have a case that the chaotic map, what kind of chaotic map we are choosing. So we're taking 2 cases, a single map or a cascaded map. Cascaded map has higher Lyapunov exponent, more complex dynamics in a sense. It diverges faster. So we are going to take both cases, single map and cascaded map. So let's look at the simplest or the most popular chaotic map, logistic map. And this is what it looks like. So it is chaotic for a small range of bifurcation parameter. And if you cascade them, the Lyapunov exponent goes higher. So, okay, so that's kind of how it works. Now, we are also going to take a 2D map called another famous 2D map, Hanon map. And we do the same thing, seed map and the cascaded map. Okay. So now, based on this, we are trying to solve the problem, and we are trying also different architecture. So first, we are going to use the single reservoir, like a normal reservoir, a parallel reservoir with masking techniques and whatnot. But then there are also recently people have been interested in hierarchical reservoir, and there is a Moon and others have recently reported this hierarchy architectural and reservoir computing system. I mean, there is a long history of this, but and we are kind of building on their work. So basically, the idea is that we have two different reservoir with two different encoding, and their outputs should be linearly independent. So you get higher dimension, uh, more diverse dimension in a sense, and then you do the readout layer. Or you can do, so this is wide or parallel reservoir. You can also do a series reservoir, or in the deep learning language, maybe called deep reservoir, which is a very hot topic right now in reservoir computing. So we tried both methods and tried to predict the thing. So we did some simulation on this thing for biomolecular memory store model and also some solid state memory store model. So solid state memory store, we used the model from Dr. Wailu's group from Michigan and Ann Arbor. And for biomolecular memory store, we used our own device model. And we kind of compared the results between different problems. And we show that the results are pretty good for our system. Of course, for physical reservoir computing, ultimate test is experimental verification, and we are working on that. But the simulation results look pretty good. Now, similarly, we did with cascaded map. Cascaded map is a more difficult problem. And as you can see, the error margin, which is measured with NRMSE, normalized root mean square error, it kind of goes up when you go from single map to multiple cascaded map. Similarly, for hand-on map, it's a more difficult problem. So this is kind of a chart where we show the results. And the good thing about this chart is that we can see that conventional RC, if you take like a hand-on map is a better problem because it needs more memory. So I'll just talk about the hand-on map a little bit. So hand-on map, you can see that the results are pretty good actually compared to what you have with, if you don't have reservoir, just a linear network, this is what you get. Compared to that, we get much better result, very low error rate. And in fact, this improves when we do wide and deep reservoir. Wide RC gives the best result in our simulation. Similarly, when we go to cascaded hand-on map, of course, the results become a little worse because it's a more difficult problem, but the same pattern we can see. So that's the thing. So it seems like having the same number of reservoir nodes, it is better to do wide reservoir than a single reservoir or even deep reservoir. But of course, it varies a little bit from problem to problem. So for example, from solid state memory store, we see that deep RC actually performs better than the wide RC. So there is no silver bullet. It has to be adjusted based on each device. So there is some limitations to this approach. So we are currently working on that, is that, if you want to predict one step or two step, it works reasonably well. But as you want to predict more and more steps, 6 or 7 steps ahead, it kind of hits a brick wall and the results are not good. Same pattern we see for logistic map and hand-on map. So so that's something that we are trying to do. It's inherently difficult in a sense that chaotic systems become very unpredictable when as you move through time. So more and more steps ahead, things become more difficult to predict. So it's difficult to resolve this problem. Now we go to another problem, second order nonlinear dynamic system. So it's a second order nonlinear dynamic system as the name says, but I'm going to shorten it to call it SONS. And we try to solve the same problem. For the sake of time, I'm not going to talk about details of this problem because I'm going to cover this multiple times. But this is kind of the main thing. You have a second order nonlinear dynamic system. You have the exact equation, but assume that you don't have the exact equation, right? So this is the motivation of the problem. You give an input, you look at the actual output, and based on that, you model the system, right? Just data-driven modeling without knowing the underlying equation. And then for a test input, random test input, you verify your model output with the actual output. So that's the idea, right? Now in this case, we actually have the equations, so we can generate the actual output, and that's how we create our model on. And then when you do the testing, we verify how good our data-driven model is. So that's the idea. We did 300 inputs. We truncate the first 50 points for transient. And then based on the remaining 250, we train our model and we tested our result. This is again parallel reservoir. So we have 9 devices and 10 different time encodings. So we have 90 reservoir states basically. And based on that, we generated some results. The results are reasonable. I mean, it was kind of a first experiment, but we improved upon it, and I'm going to show it later. So now let's move on to, we talked about memristor a while. We also did with mem capacitor. So in the mem capacitor side, we recently published this work. So we experimentally verified a mem capacitive reservoir network. So mem capacitor is again this water droplet based systems. So whenever you give input like this SONS input, each mem capacitor behaves slightly differently because of stochastic device to device variation, but also we did different time encoding as well. Anyway, so based on this, we did the prediction and the results were pretty good. As you can see, the prediction matched pretty well with the ground truth. So this is the training result and this is the testing result. And this is kind of the experimental setup. And we kind of compared with our linear network. We saw that this significantly improves compared to linear network. Now, the result summary is kind of like this. So if you do bimolecular memristor, bimolecular mem capacitor, different results you can get, and the test NMEC gets better. And bimolecular mem capacitor also, the test results experimentally gave us pretty good. With 50 reservoir states, we got 1.21 and 10 to the minus 3. And this is much better than solid state memristor. But the main thing about mem capacitor is that it is significantly less energy. The reason is that memristor is resistive. So it's always dissipating energy, right? But mem capacitor only consumes energy when the spike changes. So when there is a pulse transition, 0 to 1 or 1 to 0 kind of. So otherwise, there is no static dissipation. It's only a dynamic dissipation. It is similar to going from NMOS logic to CMOS logic. So in NMOS logic, it was always static loss. For ideal CMOS logic, there is supposed to be no static loss, right? So that is the kind of going from memristor to mem capacitor. It's a little bit more difficult in reality to build fully scaled hardware around this. But if we can do this, so this is one thing we wanted to kind of champion in this paper is that mem capacitor has this inherent significant orders of magnitude energy advantage if we can build scalable systems with mem capacitive devices, right? So even for edge computing, like you don't need to build a huge thing, right? You can build small things which consume significantly less energy, which is important for resource constrained systems. So we kind of show this more detailed with a chart later. So let me skip a few slides just to emphasize this point. Yeah, so this is the chart that we showed, and we kind of compared power consumption and energy per spike. And as you can see that our work, the power and energy is significantly less compared to previous works. So we compared the state of the art, like last few years, five memristive work, and we show that mem capacitive way of doing things is significantly more energy efficient. Okay, so I am going. Yeah, so there are a few other problems that we solved, but I'm not going to go into the details. One problem is spoken digit classification. Basically, there are 5 speakers. They are saying 10 times 0 to 9, and we are trying to classify this spoken digit. This is a temporal problem because audio signal is temporal. And also we solved this using mem capacitor. And we got relatively pretty good results, to be honest, with our experimental results. And again, recently published work. Similarly, we solved another useful problem, EEG signal. So this is, we wanted to show real-time signal processing, temporal signal processing for health application, which we think is a good application for our device, biomolecular device, because it has good biocompatibility. And we came up with a simple way to do EEG signal classification and classifying patients to healthy versus epileptic. And we got very good result. I'm not going to go into the details of this. You can find this in our work. And we verified both by simulation and experiment, and we got 100% accuracy. So that was pretty good. Yeah, experimentally we got 100% accuracy. We introduced something called virtual node incorporated with feature modification, and we got 100% accuracy using this data. Okay, so now iris data is of course a very famous benchmark problem, but classifying iris flowers, but I'm not going to go into that. I'm just going to introduce one last idea. So this is very recently came out in SEECS Applied Materials and Interfaces. So this is our most recent work. This one is with memristor. The idea is of heterogeneous reservoir. So as we mentioned earlier, we are replacing this recurrent neural network with dynamic physical systems. And in our case, we have parallel devices, parallel memristive or mem capacitive devices. But we do different techniques to make sure the output nodes are different. But we thought that instead of doing those techniques in the input side, what if we have separate different devices, which has different dynamics? Can we do that? So a simple way, we in this paper, we call this heterogeneous reservoir. And we tried two different techniques. One is that we changed the concentration of the LMNCSM peptide. Another thing we did is that we changed the voltage amplitude, because our device, what happens is that its dynamics depends both on lipid concentration or LMNCSM concentration, peptide concentration, or it also depends on the time constant, also depends on the applied voltage level. So by just changing bias or changing the concentration, you can change the dynamics. So we tried both. And this is where we are showing that as you increase the ALM concentration, the paired parts facilitation, PPF percentage changes, as you can see. So we tried 5 different concentration, and as you can see, the dynamics changes. So we tested this for different fitting. We fitted all the parameters for 5 different concentration. We characterized the response of these devices. And based on this, we solved the same SONGS problem. And this time around, we found something very interesting, is that with 5 devices, only 5 devices, we got experimental testing NMSE value of 1.5 into 10 to the power minus 3. Whereas in previously metal oxide based memristors, there was 90 devices that were used, homogeneous reservoir. So we are using heterogeneous method. With homogeneous technique, 90 metal oxide memristors got 3.13 into 10 to the power minus 3. So we got twice, our accuracy improved by almost, reduced the error by 50%, with like 16 times or 18 times less devices. We explain the same idea with bias, as we mentioned. It also depends on amplitude. And we solved a problem called neural activity classification. So there are 4 types of neural activity we consider: tonic, bursting, irregular, and adapting. And we solved this problem by having only 3 separate heterogeneous reservoir with 3 different voltage offset. And we solved the problem. Basically, the summary is this, that we got 96.5% experimental testing accuracy with only 8 trained parameters. Compared with the previous work on this task, state of the art, with a single memristor, that error rate was reduced from 13% to 3.5%. Also reduced the number of trained parameters from 128 to 80. So that's kind of the summary of our recent results. So now I'm going to talk about the remaining few minutes. I'm going to pose a few questions that I am thinking about, and I think would be interesting for the whole Ph.D. community to think about. So this is the recent book I mentioned. There is a chapter from one of the pioneers, Wolfgang Mass, who came up with liquid state machine. So they considered a liquid state machine architectural level and posed this question, that right now the way we are doing this thing is that we build a reservoir and then we try to find out the linear readout weights. And if we find a good weight, we say that we have solved the problem. But is there a more systematic way to do this? Can we optimize the reservoir sum? somehow. And this is what they call that reservoirs learn to learn. And they make a distinction between inner loop and outer loop. So in the inner loop, what we're doing right now, but can we do an optimization on the outer loop where we even these, reservoir connections and input connections, those things are now hyperparameters, and we can optimize that. And they show a method to do that. And they show very good results with this. Now, my question that I'm thinking is important for our community is that, can we learn something from this, from liquid state machine, how reservoirs learn to learn, and do this in physical reservoir? Can we reconfigure our physical reservoir from some using similar techniques? So that's something to explore, I think, in the coming days. Another thing is very popular now is deep learning, and similarly for reservoir, doing deep reservoir computing. So instead of a single reservoir, how about we stack multiple reservoir and combine them? So there is a recent work. In fact, Galicio and Micheli, they have been working on this for a while now. They have several seminal papers on this. But this is from the book that I mentioned, the book chapter they wrote. And this architecture, it's not trivial how we can do this in physical reservoir because each substrate is different. But if we can come up with substrates that are easily cascadable, would it be advantageous to do this? We previously showed that when you do deep reservoir using memory strip device, we got better result, but that was in simulation. In experimentally, how to do this, it's not yet clear, but I think that's an interesting direction. Deep reservoir computing is going to be an interesting direction. Another question, so this is a conjecture that is floating around in the literature for a while. It's called edge of chaos or edge of stability. So basically the idea is this, that reservoir is a nonlinear dynamic system and it can lead to chaos, but it's the input driven system. So chaos is probably not the better word. Probably the better word is stability. So basically, if there is a parameter, let's say G, scaling factor in the reservoir, if you keep changing G, the conditional Lyapunov exponent is going from negative to positive. Now, if it becomes positive, it's chaotic response. So it's not predictable anymore. So it's not good as a reservoir. However, if it is too negative, it's too stable, and that's not good either. So the hypothesis is that the reservoir X best when the lambda is close to 0, but still less than 0. Okay. And there are some good like examples that show with NMSC value for certain problems that when it is close to this edge of stability or chaos, it performs well. There is some controversy in the field still about this because for some problems it does not hold, but I think this is something we need to look into. Another question is memory nonlinearity trade-off. This is well known for a while now, is that if you increase the memory in a system, it messes up with the nonlinearity. It's difficult to get both of them right. So to be a reservoir, you need usually both. You need memory and you need nonlinearity. And usually one hurts the other. So how can you get the best of both worlds? So there is this recent work by these authors mentioned earlier in the below. And they show something called a mixture reservoir. So they have some linear nodes and some non-linear nodes. And the percentage of nonlinearity is shown as P here. And they show for a certain problem. So the x-axis is kind of a measure of the nonlinearity and y-axis is the measure of memory. So in the middle part, they show that this mixture reservoirs work best instead of fully linear or fully nonlinear. So usually we have been doing fully nonlinear. All the neurons are nonlinear neurons. On the extreme side, you can do all linear neurons, but then you don't have any nonlinear. But mixture reservoir apparently has the best of both worlds, at least for certain classes of problems that they have shown. But this is something that in the Ph.D. community, how do you do that? Because it's not obvious how to do this in physical reservoir computing. So basically what I'm saying is that a lot of algorithm and architectural development and the software reservoir computing and how to translate them to physical substrate is something we need to seriously take instead of ad hoc method right now that, finding one problem and solving it, like more systematic way to assess the quality. So another thing that recently came out is information processing capacity. This is a sequel of the 2012 paper that came out last year. So it's a very sophisticated information processing capacity of a reservoir. I have not seen in the Ph.D. community to use this kind of assessment metric. So myself, in our group and other groups, I think we should look into this kind of metrics, benchmark physical reservoirs, so that there is a global comparison against different reservoirs. So, we can fairly assess them instead of ad hoc problems, because then it's difficult to compare them. So I think that's kind of benchmarking. We are now, I think, a little bit more matured. Over the last 10 years, there is a lot of work. Now we need to do some assessment and benchmarking, and this has become more important right now, I think. So this is what I think is the future trend for physical reservoir computing. With that, I am going to conclude my talk and open the floor for questions.
Thank you, Dr. Sakib. Great presentation. I'd like to encourage everyone to post their questions in the Q&A below. I had a few questions on, I think it was slide 21. You showed the results for both biological and solid state, and it looked like it really depended on the test, which one performed better. Do you have any insights into why this one?
This one?
This one, 22, I was wrong. The test.
No, I think, I think basically this is simulation based. So this biomolecular memristor and solid state memristor, their physical composition is very different, but the actual dynamics is not that different. So
that was kind of my follow-up question. Are they functionally the same or not?
Their dynamics is very similar.
Okay.
They are both first order memristor. They are all both described by first order differential equation. They are made very differently. One is oxide based solid state, like tungsten oxide and all that, and one is lipid based water droplet. But as far as the underlying math is concerned, basically.
Okay. What do you think explains the different results then?
So a lot of this depends on voltage encoding. So different voltage range, these devices act differently. So these results are kind of ad hoc optimization, but there is no guarantee that these are the final most optimized result for this. So it is very possible that, for example, here you see that this is slightly better. The solid state result is slightly better than biomolecular result. But it is possible that there is some other space, some other voltage encoding for biomolecular memristor where this number would be comparable to this number. So it's a little bit ad hoc, as I mentioned earlier, the way we are doing this.
Okay, and then one other question I had with the biomolecular components based on phospholipids.
I just want to mention one thing. One problem is that this is little bit shooting in the blind. So we try different things, and one of them sticks and it works. So oftentimes we are not even sure that why it works. So I just wanted to be.
Thank you. With the phospholipid-based circuit components, how much of an issue is their long-term stability and structural integrity?
Yeah, that's a problem. I mean, so far we have been able to design the systems which are pretty stable as far as phospholipid membranes. There's a lot of research going on in Dr. Nazim's lab to make them more durable, but it's not, of course, as durable as solid state devices.
Okay. Thank you. An anonymous attendee says, thank you for the wonderful presentation. Could you please shed some light on the method used for audio signal encoding methods that help yield good results in audio digit data set?
Okay, let me go into that. Yeah, I didn't have enough time to go into this. So basically, this is a standard data set that we got, is available. Each spoken digit is differentiated into different frequency channel, and then there are 40 time steps. So there are 50 frequency channels and 40 time steps. So there are 50 times 40 or 2000 pixels, as you can think of that as for this spoken channel. We have binarized this information. So each pixel is either 0 or 1. Okay. So now based on this, what we do is that we take one channel and this sequence of zeros and ones, we pass it through our mem resistor or mem capacitor, whatever our memory element is. Now 0 and 1, you have to make a decision that how are you going to encode them into voltages, because these are voltage driven systems. So for example, in our case, for MEM capacitor device, the way we have encoded it is that 0 is 10 millivolt and 1 is 200 millivolt, because that's the range it works best for MEM capacitor. For MEM resistor, we would have probably chosen a different range. Maybe it would have been 20 millivolt to 130 millivolt, because that's a good range for our MEM resistor devices. So it's a little bit of an art. You have to do some searching and find out what is the best amplitude encoding for your specific physical substrate. And then, we just run these ones and zeros through this device, measure the capacitance at the end of each pulse, and you can see that capacitance keep increasing or decreasing based on the sequence. And these capacitances are the reservoir states. So in this case, you have to make a decision that after how many time steps we are going to take the capacitance. So based on that, you will have a certain number of reservoir states in this particular problem. So in our case, we have taken, I think after 5 virtual node, we have taken 5 time steps, we have taken 1 capacitance. So for 1 channel, we got 8 MEM capacitance or capacitances. So for 50 channels, we have 50 times 8 or 400 reservoir states. Based on this 400 reservoir states, we do the classification. They are the features for our readout layer, that whether this particular digit belongs to 0 to 0 to 9, which one it is. So that's that problem setup. Is it clear, or does it answer you?
Thank you. And there's just time. I'm going to end on the questions. Thank you again, Dr. Sakib, for a great presentation. You'll be receiving a plaque from the Center for Cybersecurity and a certificate of appreciation. We'll be in touch.
Thank you so much.
Bye.
Have a nice day.